Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve a thermomechanical analysis and we are going to validate with the analytical result. So in this case, I have taken a bar of 1 meter length and breadth and height are 0.1 meter and 0.1 meter. It has a made up of steel with an Young's modulus of 210 gigapascal and Poisson ratio is 0.3 and thermal expansion is 12 e power minus 6 1 by Kelvin. Density of this material is 7860 and thermal conductivity is 40 watt per meter Kelvin. Now we'll see the boundary condition. In previous case, we have solved by applying temperature difference of one side and 373 Kelvin and another side we have given 473 Kelvin. In this case, what we are going to do, initial or reference temperature is 293 Kelvin. That means atmospheric temperature which is taken 20 degrees Celsius. Then all the external surface all are 30 degrees Celsius. Due to the temperature difference, it's trying to expand, but we are arresting the expansion by applying the fixed boundary conditions. In both the side, here we are fixing dx, dy and dz. All the translation degree of freedom we are arresting here. Here we are only arresting only dx. Okay. In this case, we can apply simple problem of thermal stress is equal to Young's modulus into temperature difference delta T into thermal expansion. As we can see, Young's modulus is 210 gigapascal and delta T is, here you can see, delta T is just 10 Kelvin. And thermal expansion is 12 into 10 power minus 6. By applying this into the formula, we'll get the value of 2.52 into 10 power 7. It's nothing but 25 megapascal. Now we'll check the value of, yes, Young's modulus value is correct. Now we are getting 2.52 into 10 power 7 Pascal. Now we'll solve the problem. We'll check the result with the analytical value. Now I have opened salome meca. As you can see, first we'll model the geometry using geometry model. First go to geometry model. As our geometry is very simple, just go to new entity, primitives, box, x length is 1, y is 0.1 and z also 0.1. Just apply and close. Now we have modeled our geometry. Now we'll create a groups to apply the boundary conditions. Here you can see, here and here we have to fix it separately. And all the surface we have to apply 303 Kelvin. 3 groups we have to create. First one, face group. Select this face, add. This one is fixed in X, Y, Z. Just apply. Here, just add it. Fix X. And all the other surface, we can select one by one also, or we can go for select all. Select these two. We have to remove these two only. Remove it. Now this 4 surface, just name it as temperature. Anything we can give. I'm just giving a temperature. Just apply and close. Now you can see these 4 faces selected. and this one is right side face, this one is the left side face. Now we can save this model. Just file, save as. Simply you just navigate this file into where you want to save. This is the second case of thermomechanical. I'm just saving here. Now we'll create a mesh for solving. Just go to mesh model, select this mesh, go to create mesh. This is a simple cubic geometry. We can create hexa element. Just choose the algorithm as hexahedron. In 2D algorithm also you can choose quadrangle mapping. In 1D algorithm, wire discretization. In hypothesis you choose local length. Here I am just specifying 0.02. Just say OK and apply and close. Now we can generate the mesh. Right click, compute. Now it has generated the hexahedron element with a linear element of hexahedron with 1250 elements. It has a surface element 1050 elements. It has 1836 nodes. Okay, just close it. Now we can save this file. Here you can check the groups are available in this mesh. Now the groups are available in the mesh as a elemental groups. Now we can go for aster study to create the set. In the previous case, we are not used the time step to solve. Same case we can use the time step to solve the problem. Now just right click, add a stage with assistant. This one is the thermomechanical analysis. This one I have explained already. Just go to next. Again you just go to next. This is the 3D model. Here it is a 40. Thermal expansion is 12 e power minus 6. This is, you keep it 0. Just go to next. Impose the temperature on the groups. Now temperature, we have to apply temperature of 303 Kelvin. Here you can see all the surfaces, outer surfaces 303 Kelvin. Just go to next. There is no heat flux. Go to next. There is no volumetric heat source also. Initial temperature, it is a 293 Kelvin. Just go to next. Initial temperature is not required because we are not going to do transition analysis. Now thermomechanical discretization it is asking. First one is 0, 1 we can give. What it will do, it will solve the solver, static thermal solver with 0, 1. When time is 0, it will not apply any load. When time is 1, it will apply all the loads. That is the way it will solve. Just go to next. Again go to next. Now impose the degree of freedom. As you can see it here, one side surface we have to fix all directional displacement 0. Another side we have to fix only dx only fixed. Now we can choose one by one. Fix xyz. I just want to fix all. Then fix x. I just want to only fix in x direction. Just go to next. There is no pressure load, but anyway without applying pressure load we cannot go next step. See here it will ask to apply the pressure load. For that you just apply the load, then we'll delete it. So dummy load I'm applying it. Now we'll save this file. Finish it. Now it has generated thermomechanical step. First it is reading the mesh, then it is defining the thermal model, then it is a mechanical model. Material property, here rho Cp is not required. If you want to remove this also you can remove it. I'm just removing it. Just enter thermal, edit, just OK, just apply and OK. Now after defining the material, here you can see, so the necessity property are alpha, thermal expansion, Young's modulus, Poisson ratio, and lambda. These are the necessary essential properties. Rho Cp is not essential for thermomechanical analysis. If you want to solve transient analysis, that Rho Cp is required. If you are doing dynamic analysis or model analysis, density is required. For static analysis, density is not an essential property. So these 4 properties essential to do the thermomechanical analysis. Now we have to assign this material property to the model. Then function list is 0, 1. What it will do? When time step is 0, there is no load. When time step is 1, it will apply all the boundary conditions. That is the way it will do. For that only it is definitely. First load step is temperature load, then is a mechanical load. Pressure load, it's not necessary, just delete it. Now here you just go to thermal. Here it is showing initial condition, it is not at all required. Time step it is required, just apply and OK. Then material, here you can see external temperature. Here reference value, it has to be 293 Kelvin. Then we are imposing the thermal result to the model to do the mechanical analysis. So here you have to choose thermal solver result. So after that we have to do mechanical analysis. It is a linear mechanical, that means static solver. Time step list is required. This second one is the pressure load. This has to be removed because we have deleted the pressure load boundary conditions. Just apply and OK. Now we have corrected all. Outputs also it is saving. What it will, mechanical solver, it will calculate only the displacement. To calculate or to see the stress value, we have to do post processing. Just go to post processing, call champ. Here it is coming unnamed, so use the previous name. Here thermic it is showing, we have to choose mechanical solver. From that we have to calculate. First one is sigma L0, second one is sigma nodal value, SAEQ L0, SAEQ nodal value. From the element only it will calculate nodal value. Just apply and OK. So now we have calculated stress values from the solver. Then this value has to be saved. So we have to modify this output file. Just go here. Instead of meca static, we have to choose call champ. Just OK. And also here there is an option called tau champ. Make it yes. Just OK. Just apply and OK. So now everything I have set. Just save it. Only thing, previous case we have deleted this list ER. We can keep this list here, list also. Only thing is it will solve the static analysis in a time step, pseudo time step. When time is 0, it will not apply any load. When time is 1, it will apply all the loads. That is the way it will solve for thermal analysis as well as the mechanical analysis. Now just go to history view, save this file. I'm just giving more memory of 4048. Here auto refresh making into 5 seconds. Here also we can change the solver. 15.6 is the stable solver. Just run it. Just wait for a while. It will show if any error comes. Yes, now it is showing some error. Just scroll down here. Yes, we have specified list ER. It is solving as a transient kind of thing. That's why it is asking for Rho Cp. So now we'll delete that one. We'll do the static analysis. Just go to the case view. We'll delete this str. This is not necessary. Now we have deleted here. So that's why after that, wherever you have used, here it is showing time step. That means it is taking into a transient. So it is require row CP. That's why that is the value it's showing. So I'm just deleted. Here also I'm just removed. So it is do static analysis only we are required to do. Now just save this file. We'll solve it. Just wait for a while. If any error comes, it will show. Here you can see it is finished almost. Yes. Now it is solved without any error. Now we can open the result file in paraview to do the post processing. Just go to paraview. Paraview is the wonderful post processing tool. Just select this built-in and open it. Just navigate the folder where your case is located. This is the second case. This one is the file. Just open it. Just apply. Here itself you can see we have a thermal result as well as the displacement. First we'll see the thermal result. Just apply temperature. Because we are applied a temperature of 303 Kelvin, so all are it is showing 303 Kelvin. Okay, now we'll see the displacement. Just apply, just go to the displacement value. Now you can see from the reference temperature and the body, all the surface we are applying the temperature. Due to that it has a displacement. So this one is the displacement in x direction. I'm just changing this into blue to red rainbow with 12. So this is the displacement x. This one is the displacement y. Displacement z, because it is expanding in all the direction. Due to the temperature difference, it is expanding in x, y, z. Now we will see the stress value in x direction. Sigma, this one is the sigma magnitude. Change this into sigma x. Now we'll check the value here. Select this over point and locate it away from the boundary condition. Here we are getting in the SIEQ, not SIEQ, actually SIGM underscore NOEU. The first value you can check it, minus 2.56105 e power 7 we are getting. Okay, so this is nothing but here we are getting is a 2.52 e power 7. We are almost getting this same value. Here we are getting 2.52. Here we are getting minus 2.57. That is because of it is in the compressive stress. We are arresting here and here due to the arrest boundary condition. Here we are getting high stress. So we have to check the result away from the boundary conditions. So for that, what we can do, we can select the element here. Just go to filter, search, type extract selection, just enter it, just apply it. Now we have extracted this location. Now we have to check the value here. Just we have to rescale the data over all the time step. Just automatic rescaling. Now it will show the stress value in this particular location. Here the stress value is almost closer to the value of 2.56 minus 2.56. So this value we can compare with the analytical value. So here only, which is very close, the error difference is also very less. So this is the way we can compare the result with the analytical data. Now similarly we can check with the von Mises also. Von Mises, it will not show the negative value. If you want to see the negative also we can go for von Mises signed. Here you can see minus 2.56. This is the signed von Mises stress. So this is the normal von Mises stress. This will come as a positive data. So to view full model, just delete this previous one, extract selection, you will get the full model. Now again do the rescale and disable automatic scaling and take care. Here also we can change the color, make it blue, rainbow, blue to red, just apply and close. This is just make it into 12. So this is the way it will do. Now we can see the expansion, how it is expanding. Now just click this wrap back vector, just apply it. Now give some scale, just apply. See, it is expanding in all the direction. Because of arresting here, it will not expand here. Here also it is expand in y and z direction, not in x direction, because we have arrested here. Due to that only it is generating the stress. Now we can animate it also. Instead of this value, we can give some 215 frame. Just say OK. Now we can do the animation. I will give 200. Edit the animation track. 1000 I'm just giving. Now we'll animate. Loop we can make it and animate. So this is the way it will expand. It cannot expand in x direction because we are arrested here, and here we have arrested completely. That's why we are getting very high stress closer to the boundary condition. So wherever we are calculating analytical data, that value we have to check away from the boundary conditions. This value is coming very closer to 252 megapascal. That is we are getting from analytical data. 25.2 megapascal. Sorry. So in this way we can do thermomechanical analysis of a bar. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.